So holomorphic vector bundles and Hermitian metrics. So if we have a complex manifold, we consider a vector bundle, a C vector bundle over it. And I have recalled the definition at one of the previous lectures, probably I didn't spell explicitly what it means for a vector bundle to be holomorphic. So E is holomorphic if it is defined by a cocycle where the functions that give this cocycle are holomorphic. So and if we have such a holomorphic vector bundle, so let's do the following thing. Let's take some section over some open subset. So E holomorphic vector bundle. Let's take a section and let's assume that well, let's just say that this section is defined by a collection of maps into CK on the open covering of this open set U. So S is given by a collection of S alphas that are just maps from the intersection of U and U alpha to CK. So the rank of my vector bundle is K, such that we have the following condition, right? So that's a definition of a section for all x in the intersection of U alpha, beta, and U. And then let's apply del bar operator to this section. So I don't assume S to be holomorphic, right? So we do not assume S holomorphic. So it's just a C infinity function. But then I can write the components of this S alpha and apply to them the del bar operator. And then, well, I get some collection of 0, 1 forms, del bar S alpha 1 and so on, del bar S alpha K. These are just 0, 1 forms on this open set U intersected with U alpha. And if now I look at this equality, then I observe that del bar S alpha will be mu alpha beta dot del bar S beta, right? Because this mu alpha beta is holomorphic. And this means that this del bar of S alpha, so this collection, gives me a section also of a vector bundle, which is now this lambda 0, 1 twisted by E. So we have a well-defined section. I will denote this section like this. It's a section of lambda 0, 1 m times E. And obviously we have some Leibniz rule, which is easy to check. So if I just apply this del bar to each component, then, well, you can see that this is del bar F tensor S plus F del bar E S. So that's quite clear. So check this as an exercise. But then we can extend this del bar operator. So we have such a well-defined operator. It's a morphism of sheaves of C vector spaces. Right? We can extend it by Leibniz rule. Namely, so it will map lambda pq m tensor E into lambda pq plus 1 m tensor E. It's clear how to extend this operator. So if I apply it to the one form tensor some section, then I get del bar alpha tensor S plus, well, here we should remember that there is some sign rule, which it works as usual when you apply this exterior differentiation to differential forms. If you exchange the operator and the K form, then they should be multiplied by the degree of this form. So in this case it will be P plus Q alpha wedge del bar E S. So this wedge product means that, so here I have a PQ form, and this is 0, 1 form tensor section of E. So I can take the wedge product of this of the PQ form and the component of this tensor product, which is the 0, 1 form. So that is denoted like this. Okay, so that's the usual way to extend this operator, and then one can check also. It's quite obvious that if I do this, then this extension satisfies the following property, that its square is 0. And conversely, so actually, if I have now a C vector bundle, conversely, so given a complex vector bundle with an operator del bar E, like this one, right? So as in star, that satisfies Leibniz rule. And whose square is 0 when we extend it in the following, in the same way as we extended this del bar E. So then, okay, I have this vector bundle with this operator, and then there is a theorem. So we can prove that this E actually carries a structure of a holomorphic vector bundle. It's similar to this theorem we discussed last time of Newlander and Nuremberg, in the sense that it constructs some kind of a holomorphic trivialization of a bundle from the existence of some additional data. In this case, this del bar operator that satisfies this condition. So the theorem is attributed usually to Cauchy and Malgrange. So E, as above, admits a structure of a holomorphic vector bundle such that this del bar E is the corresponding operator, corresponding holomorphic structure operator. Okay. So I will not prove this, and because that proof is essentially similar to what we did last time. Actually, maybe this theorem is a bit easier. So to prove the theorem, what one actually needs is to construct some holomorphic sections. To prove the theorem, one needs to show that E is locally spanned by holomorphic sections. So the section is holomorphic S in E such that del bar ES vanishes. So that's the definition of a holomorphic section. Well, if E is real analytic, so recall that last time we considered this case of real analytic manifolds and then worked with power series, and here one can use the same thing. And also in the case when M is one-dimensional, this theorem is a bit easier, so I put this into the exercises. Okay, so for the people who are present here, there are some exercises, and I will later put them onto the web page, so that you can you can find, or probably I'll also make I'll write in the email so where to find them. Okay, so let's look at some examples. So are there any questions about this? Okay. So well, if we have now complex manifold, then of course we have the usual del bar operator, and it actually gives us the structure of a complex of a holomorphic bundle on some of the bundles that we have considered before. So recall that we have decomposed the Durand differential into two parts, and we have the following condition that d squared is 0. On the other hand, we can write it, decompose this d squared also into components, so we'll have del squared plus del bar plus del bar del plus del bar squared. And these are components of different types, so this is type 2, 0, this is type 1, 1, and this is type 0, 2. So they all have to vanish, and this implies that so this del bar operator satisfies the condition that its square is 0, and there are two other equalities like this. So this means that well, lambda 1, 0, m is a holomorphic vector bundle. Well, of course, it is also possible to check this using the definition in terms of cocycles. So similarly, the bundles lambda p 0 m and t1 0 m, so they're all holomorphic. So that's just the exterior power of a holomorphic bundle, and this one is the dual of a holomorphic bundle, so they are all holomorphic. And we will write, so I'll try to distinguish between bundle and the space of holomorphic and somehow the sheaf of holomorphic sections. So E is a holomorphic vector bundle, then I'll write curly E for the sheaf of holomorphic sections of E. In particular, so this lambda pm, so the sheaf of holomorphic sections of lambda pm will be denoted omega p m. So omega pm, and for that t10 I'll write it like this, so curly tm. So these are sheaves of holomorphic sections of lambda p0 and t10. And if the dimension of M, the complex dimension, is M, then this bundle omega M, so this bundle has a name, it's called the sheaf, so somehow you can always identify the locally free sheaf of OM modules with holomorphic vector bundles, so I'll talk about somehow these objects as bundles also. So this thing is called the canonical bundle, so this is the top exterior power of lambda of omega 1, right? So this is called the canonical bundle and denoted by Km. So let's look at more examples of vector bundles. So let's take CPN, for example, with homogeneous coordinates x0 and so on xn. And let's define a cocycle. So we have this covering ui is the open set of all points such that xi is not 0. And let's define the cocycle mu ij of x equal to xj divided by xi. So this is a function from uij into c star, holomorphic function obviously, and the corresponding bundle is, or rather the sheaf of its holomorphic sections is denoted by O of 1. So that's the definition of O of 1 if you want, or you can define it in many other ways. So it's a line bundle over CPN, and well, let's construct some sections of this line bundle. So if we have some polynomial of degree 1 in the variables x0, xn, then we can construct a section of this bundle. So let's do this. So if P equals the sum of ai xi, so we let Si of x be P divided by xi. Right, okay, so let me rename the index here. So this is j goes from 0 to n. So I take this linear form and I consider the following function on ui, and then this obviously satisfies the following relation that Si of x equals, so if I multiply this by, well, if I take mu ij of x, this is xj divided by xi, and then if I multiply by sj, then I have this equality. So this really gives me a section. So we'll also use, yeah, okay, so this means that we already have n plus 1 linear independent sections of this vector bundle. So x0, xn, they all give me sections, so we get the following morphism of vector bundles. So a section, we may view a section as a morphism from the structure sheaf to a vector bundle, right? So, and here I have several such morphisms, and I produce out of them the following map. So O goes to O of 1 direct sum n plus 1 copies. So this is just given by all those linear forms x0 up to xn. So one can check that this is actually an embedding pointwise, so as an exercise. Well, I mean, it's kind of obvious just because there is no point in the projective space where all these coordinates vanish, so I don't even write it as an exercise. So this is pointwise an embedding, and well, so does anybody know what is the quotient?
Tautological? No.
Well, the tautological is usually denoted by O of minus 1.
Yes.
And this is by definition O of 1 dual.
There is a dimensional problem with tautological.
Yeah, right. So let's think about it. So the quotient, so we have in this one.
It should be tangent bundle of.
Yeah, exactly. You're right. So this is the tangent bundle. And how to see this?
Well, I guess you can show that the usual isomorphism between tangent bundle and home from O of minus 1 to its orthogonal is homomorphic.
Yeah, right. Well, I mean, there are many ways. Actually, it's a bit tricky. So then since not everybody is familiar with this, so let's do it. Actually, there are different proofs of this, and some of them are quite computationally complicated. So I want to show you one proof. So let's prove that the quotient is the tangent bundle of CPM. But before we do this, so let's discuss one other thing. So first of all, yeah, so let's finish with the notation. So the notation is like this. So O of minus 1 is the O of 1 dual, and also O of k is just the tensor power of several copies of O of 1 if k is bigger than 0, or O of minus 1 if k is less than 0. Well, then I should write minus k if k is less than 0. And if E is a bundle, then this thing is by definition is just tensor product like this. So that's just notation. And let's now talk a bit about the normal bundle of a sub-manifold. So if we have a sub-manifold, I want to call it Z in M, a complex sub-manifold. Well, we then have the following sequence. Well, the normal bundle is defined as usual, so we can restrict the tangent bundle of M to Z, and it will contain the tangent bundle of Z as a sub-bundle. So let me write these sheaves of holomorphic sections here. So like this, Tm restricted to Z, and then the quotient is by definition the normal bundle of Z in M. So this is the normal bundle. And let's assume now that this Z is given as a zero locus of a section of some holomorphic vector bundle over M. Assume E is a holomorphic vector bundle over M. S is a section. And assume that Z is the zero locus of this section. And also assume that this section is regular in the following sense: that if I take a point, let's say the rank of E is, for example, R. So if I look at a point in Z, then if I trivialize my bundle in the neighborhood of this point, then this section is given just by several holomorphic functions, and I want the differential of this, the map given by those functions. I want the differential to be of rank R. So is of rank R. So this condition in particular implies that Z is smooth, and conversely, you may ask that Z is a smooth submanifold of codimension R, and then this condition will be satisfied. So in this case, if we take, if we choose some local coordinates, so locally, this E,
So we want to prove that M is isomorphic to E.
Yeah, to the restriction of E to Z. So, locally we may choose coordinates. So let's call them somehow x1, xm, such that this section S of x is given just, for example, by the last R coordinates. So this will be x m minus R plus 1, etc. xm. And then if we choose such coordinate systems around every point of Z, then the transition functions, so let's say the transition functions.
Do you want these coordinates to be holomorphic? Or?
Sorry? Yeah, the coordinates are holomorphic. Right, so this is holomorphic. Okay, yes, sorry, I haven't written this. Well, let's just do it like this. So this is the sheaf of holomorphic sections of some E. So let's do it like this.
No, I mean, these are coordinates of what?
Around X, around this point X.
Okay,
on
so
M.
These are in M. Correct?
Yes, coordinates in M. So that's a point in M. So if we have some other coordinates, for example, y1 and so on, ym, also such that the section in these coordinates is given by the last ones. So ym minus r plus 1 and so on, ym. Now then this s in the new coordinates will be given by will differ from this s. So let's call this, for example, as this coordinate neighborhood will be called as alpha, and this one as beta. So I mean, okay, so the coordinates are in some open subset U alpha in M. Then in this coordinate, this open subset, my bundle trivializes, and this section is given just by R holomorphic functions, and I may choose the coordinates because of this condition that the rank is maximal of the differential. I may choose this coordinate system in such a way that the components of this map S alpha are just the several of the sum of the coordinate functions. For example, the last R coordinate functions. And I may cover my Z by such coordinate systems. So, for example, this will be in Y beta, and then S alpha and S beta are related by some coordinate change. Well, X. So I want to write that X I is a function of Y, and but moreover, since we have chosen these coordinate systems in such a way that this last R coordinates are just given by this section of this vector bundle, these last coordinates are related by some linear transformation, by this cocycle. So well, let me write it like this. Well, the point is that if I now compute the differential of this map given by the functions phi I, so if I compute this matrix of partial derivatives for this coordinate change, then first of all, my change of coordinates preserves the subspace given by the vanishing of the last R coordinates. So this means that actually, this matrix will have the following form. So there will be something in the top left corner, then this here will be 0, and here this J1, so there will be some other block J1, and this J1 will be exactly given by the cocycle defining this vector bundle E. So this J1 is the cocycle defining E restricted to Z. So, well, what does this mean in terms of our vector bundle? So this whole matrix, it gives me a cocycle defining this restriction of the tangent bundle of M to Z. Then this thing J0, so J0 is the cocycle defining TZ. So recall that if I look, okay, so once again, so how did I choose these coordinates? So I have chosen them in such a way that the last R coordinates give me the section of my vector bundle. So this means that Z in these coordinates is given by just the condition. So these are X in this U alpha such that X are M minus R plus 1 and so on, that they vanish. Xm, that they are equal to 0, right? And then x1 up to xm minus r are local coordinates on Z, right? And so then these are local coordinates on z, and the same about this other coordinate system consisting of y's. So then if I look at this piece of the Jacobi matrix, which is in this top left corner, then this will be exactly somehow the coordinate change for these local coordinates on z. Okay, so we have this matrix of this form. So that's actually exactly, this top left corner exactly means that Tz is a sub-bundle of this Tm restricted to z, and the quotient is by definition the normal bundle, but then this implies that this quotient n z in M is isomorphic to E restricted to z. So the upshot is just this isomorphism. So let's now apply this to the following situation. So let's take M and embed it diagonally into M times M. So then that's a smooth submanifold, okay, so the tangent bundle to this product is isomorphic to, well, let's take the two projections from M times M, so P1 and P2 are two projections. And the tangent bundle here is just isomorphic to the pullback of the tangent bundle from one side plus the pullback of the tangent bundle from the other side via these two projections. So then the tangent bundle of the diagonal is of course isomorphic to Tm, so this is embedded. Well, now, okay, so now I want to write this conormal sequence, so this one. So I need to restrict this thing to the diagonal. So this is the same as pulling back via delta. So the composition of this delta and each of the projections is the identity. So I have here two identity maps. So in the middle I just get the direct sum of two copies of Tm. And this is embedded diagonally here. So the conclusion is that actually, well, that's the normal bundle of the diagonal, which is isomorphic to Tm. And it's not always the case that the diagonal is given by the vanishing of some section of some vector bundle, but for the projective space it is the case. So now consider M equal to the complex projective space. So let me explain how to construct the section and which vector bundle to take on the product in such a way that the zero locus of this section will be exactly the diagonal. So we do the following thing. We look at Cpn times Cpn, and we okay. So we recall that. So from here we have two projections as before. So P1 and P2. So recall our exact sequence that we have. It's still here. So this is not exact sequence, but there is this morphism that we have here. So let's call it star. So I want to twist this star by O of -1. So then I get the following sequence O of -1 goes to O, direct sum of n plus 1 copies. So now I want to pull this back via P1. And let's okay, so let's also call this the quotient. Let's call it Q. So let's call these two maps alpha and beta, for example. So let's pull back alpha via P1. So this will give me a morphism from the pullback of -1 to the pullback of the structure shift, which is itself the structure shift already, but on CPN cross CPN now. Yeah. And if I pull back the second morphism beta via P2, then I get, okay, so if I pull this back via P2, I again get this structure shift, well, several copies. And this goes to the pullback of the quotient to IP2. So now I can compose these two maps, because here these are two things, so these two things are equal, right? So I can get the I can take the composition of P2 upper star beta and P1 upper star alpha, and this will be a morphism from P1 upper star O of -1 to P2 upper star Q. So this is gamma. I can twist it again by, so I tensor it with P1 upper star O of 1, and then I get a section. So this gamma gives me a section of the vector bundle P1 upper star O of 1 tensor product P2 upper star Q. So let's call this E. And I claim that actually this section, so this will, let's call this S now. So this section, so its zero locus is exactly the diagonal. So that's the only thing that one has to check somehow in coordinates, but I won't check this. So let me leave it as an exercise. Well, this is not difficult somehow to check. So let's at least look at the rank. So this is a line bundle, and this Q has rank n. So a section, if it is regular, then it defines something of codimension n, so which is correct. So we should define the diagonal by this section.
What again is the claim about this S?
I claim that the zero locus of S is exactly the diagonal.
Сейчас, извините, можно, пожалуйста, еще раз говорить как-нибудь идейно, что произошло?
Yes, so once again, so let me just write the claim, and then I will repeat the argument again. So exercise, so check that the zero locus of S in this formula, so let's call the formula double star, is the diagonal. Inside the product of CPN times CPN. So, okay, so now let me repeat once again. So what do I want to do? So I recall this notion of the normal bundle. So it's just by definition the bundle that sits in the exact sequence, where in the middle you have the restriction of the tangent bundle of your manifold M. Then on the left hand side you have the tangent bundle of the submanifold, and then the quotient is the normal bundle, right? So I apply this to the case when my submanifold is the diagonal in M cross M, and I want to consider the case where M is CPM. Now I want to identify this normal bundle of CP, or somehow, so since this normal bundle is isomorphic to the tangent bundle here, well, because if you take somehow in this particular case, when you consider the diagonal, so you get a sequence like this, and so here is, so the tangent bundle of M is embedded into the direct sum of two copies of the tangent bundle. So then the quotient, it will obviously be isomorphic to Tm, so that's also easy to check, so let's also leave it as an exercise. So now I want to determine what is the tangent bundle of CPN, and now I claim that if I know that this diagonal is given as the zero locus of some section of some vector bundle E, then by this previous computation with this cocycle, I can identify the normal bundle with the restriction of E to the submanifold, to the diagonal in this case, right? So now my goal is to construct this curly E. This should be a vector bundle on the product of CPN, CPN times CPN, right? So, and now somehow, well, the idea is the following. So the idea is that we recall our sequence, that we have started with this sequence where we have the tautological bundle embedded into the trivial bundle. Then I call the quotient Q. So this is all over CPN. So now I do the following trick. I want to somehow, so I have two maps in this exact triple, and I want to pull back one map via P1, the projection onto the first component, and I want to pull back the other map beta via P2, which is the projection to the second component. And I observe that somehow if I do this, I just have done this here, and I obtain two maps. So this is P1 alpha, P1 upper star alpha here, and this is P2 star beta, so this map. But when I pull back the structure sheaf via any projection, then I get the structure sheaf again. Then I get the structure sheaf, and I get, if I pull back the direct sum of n plus 1 copies of the structure sheaf, I get again n plus 1 copies of the structure sheaf. So I just observe that this bundle here is isomorphic to this n plus 1 copies of the structure sheaf of the product of CPN with itself. So in particular, these two things are equal, isomorphic, or I can identify them. Well, I mean, they are isomorphic, so strictly speaking, I have to choose the isomorphism, but it doesn't matter which isomorphism I take. So, okay, so I have identified these two bundles, and now I go just like this. So I take the composition of these two maps. So since the okay, so P1 upper star alpha goes to this vector bundle, and then I go from here to P2 upper star Q. So I can take the composition. So, and then I call this composition, well, gamma, and then this means that I have a map of vector bundles like here, and then I also twist it by the pullback of O of 1 from the first component. O of minus 1 times the O of 1 is the trivial bundle, is the structure sheaf again. So here I get a morphism from the structure sheaf to this vector bundle, which now I call curly E. So I claim that this exactly is the section that gives me the diagonal, and to check this one just needs to write down this map in local coordinates. So is it clear, or are there any questions? So I don't say that it is obvious that the zero locus is the diagonal, but it's easy to check really, so you can try to do it.
Нет, спасибо.
Okay. Well, basically, you know, I mean, to check this, you just try somehow. This map is in the homogeneous coordinates. It's just given by all this x0, xn. So I introduce local coordinates on this one side. These are x0, xn, and these are y0, yn. So I first go here via this embedding, and then I project somehow. I mean, it's obvious that the points that are projected to 0 are exactly given by the condition that xi is equal to yi, just by construction. So if you think about it a little bit, then it's quite clear. So this is exactly the diagonal. Okay, so if I have this, then the conclusion is that, well, now I recall this isomorphism here, and also I recall that we had this isomorphism here. So Tm is now, well, Tcpm is now the restriction of this E to the diagonal. And so what will happen if I restrict this E to the diagonal? So now, again, the composition of the pullback via diagonal and a pullback via pi is the identity because of this commutative diagram. So, yeah. So here I should get just the tensor product of O of 1 and Q. So this is isomorphic to E twisted by 1. Oh, sorry, Q twisted by 1. Okay. So the conclusion is that Q is T, the tangent bundle of -1, and then we get this Euler sequence. Right, so this is T twisted by -1. So, more questions about this construction? All right, so then, okay. So let's then go on, and okay, there are more examples, of course, of the bundles that will be important for us. So let me just recall one last thing before we go to Hermitian metrics. So I want to recall or probably defined. So I want to talk about the Picard group. It's by definition, so M is a complex manifold, and by definition the Picard group is the group of isomorphism classes of holomorphic line bundles on M. So holomorphic line bundles on M up to isomorphism. The group the Picard group of M, and the group structure is given by tensor product. A tensor product of two line bundles will again be a line bundle, and the inverse is given by the dual bundle. So how to describe holomorphic line bundles? So we describe them by cocycles, and these cocycles are functions with values in C star in this case, because so these are line bundles. So line bundles means rank 1. Yeah, so that's the terminology. A cocycle is given by a function with values in a C star, which is holomorphic. I may say that this mu alpha beta is a section of the sheaf of invertible elements in OM. So I denote this sheaf by OM star. So OM star is the sheaf of invertible elements in OM, so invertible functions. They are pointwise non-zero, right? So for any point in their domain of definition. So this means that this cocycle, so this is really a Czech cocycle that gives me an element of some cohomology group, and the fact that I can consider bundles up to isomorphism and that I can pass to the finer coverings means that I really get an isomorphism of the Picard group with the Czech cohomology group. So this mu alpha beta is a cocycle and its class lies in H1 Czech of, well, you know this covering u alpha beta with values in the sheaf OM star, and then from here I go to Picard group. So any such class, any such cocycle gives me a line bundle, and then I can also pass to the limit over all coverings of the Czech homology group, and this is just by definition the first Czech homology of MOM star, which will be actually isomorphic to the usual sheaf cohomology M O M star. So and then you can prove that actually here, so of course by the universal property we have this map, and this will be an isomorphism. So my Picard group is just identified with this cohomology group, the sheaf cohomology of the sheaf OM star. And what we will actually use all the time is the exponential exact sequence. Exponential exact sequence.
The right hand side is just derived from the global sections, right?
Which one? This one?
Yes.
Derived, yeah, exactly, yes, that's a derived, the first derived functor of the global sections of the sheaf, on the category of the sheaves of abelian groups. Okay, so I want to consider the following sequence of sheaves on M, I take the constant sheaf with fiber Z. So well, let me denote it like this. So that underline, just not to mix it up with the so this is the notation for the constant sheaf with fiber Z. So then I have OM, and this is the natural inclusion. So any section of this sheaf is a locally constant function with which takes integer values. And in my view, of course, a constant function is holomorphic, so it gives me a section of the structure sheaf. And so from here I go by the exponential map like this. I go to OM star. Okay, so let me write it. So this E of a function is just the exponential of 2 pi I times L, right? So, and this is also surjective. So this is an exact sequence of sheaves. Why is it surjective? Because we, well, okay, so I won't write anything, so let me just spell it briefly. So, so we need to check that it is well, that the sequence is exact on the level of Stokes. So if we look at some, for example, how to check that it is surjective. So if I have some function defined in a neighborhood of some point in M, and which does not vanish at this point. So in particular, if I restrict the domain of definition of this function, then it will take values in some small open set in C, which is disjoint from 0. And on this open set, there is a well-defined logarithm. And then I can take the logarithm of this function and get some function here, and somehow by the definition, the okay, so the function I started with will be the exponential of the function I get here by the logarithm, like, right? So that's surjectivity, and similarly you can somehow locally on the level of Stokes check that this sequence is exact. Well, obviously the kernel, because somehow the kernel of this map obviously consists of functions that are, well, somehow this should be equal to 1, and this happens only if the function is locally constant and takes integer values. Okay, so that's the sequence, and then I get the non-exact sequence of cohomology groups. I take sheaf cohomology, so I will not write this whole sequence, but only only one piece, which includes the Picard group. So the Picard group is H1 of this one. So H1 I start from Z, so this will be just H1 with integral coefficients. then I get H1 of MOM, and then here I have the Picard group of M. And after that there will be H2 of Z of M with, somehow with integral coefficients. So this map is called the first Chern class. C1 of a line bundle is the first Chern class. Of L. And that's one way of defining the first Chern class of a line bundle. So we'll probably see later in the next lecture how one can define Chern classes in terms of a curvature of a connection. But right now, so well, that's what I wanted to say about the Picard group. Just to fix the notation. Okay, are there any questions about this?
Yeah, I have one. Just give me.
Yeah.
So, so here you use that the first homology with constant shift is the usual first. Well, the usual.
Yeah, right. So I hope. Okay, so I was not going to talk about shift cohomology too much.
Yeah.
So we should keep in mind that if we compute the sheaf cohomology of a constant sheaf, then for example this constant sheaf, then this will be the same as the singular cohomology with, or I mean somehow, well, actually for us you can always think about this as a sheaf cohomology. So we will also have cohomology with values in the constant sheaf with fiber R, for example, the real numbers or the complex numbers. And you can always identify this with a singular cohomology. Well, the way to do it is to write down somehow the, you know, proper resolution for the constant sheaf. And then observe that this resolution actually computes you the singular cohomology. So I won't explain this for sure, but if you don't know where to look it up, it's in this book of Wells, Differential Analysis on Manifolds or something like that. So yeah, actually, by the way, you can find the literature on the web page of this lecture course in мат-нет. So there is this book by Wells, Дифференциальное исчисление на комплексных многообразиях. So he explains this in that book, for example, and some other facts about de Rham cohomology as well. So that is not the full on exact sequence, so I should put some dots here. Of course, it's longer, but we will be probably mainly interested in this piece. And sometimes it's useful to know that one can sometimes put